From the point of understanding Ampere circuit law better, we have a small derivation. So we are trying to prove Ampere circuit law for a straight current carrying conductor. So basically, we know the law is this, right? So over the entire loop, if we integrate all the components of P and dl, the dot product between them, it should be equal to mu naught into the current enclosed by it, current passing through it. So basically what we'll do is we'll take the RHS and prove stuff. So we are trying to prove, take this up. And prove the RHS. Now let's look at the derivation, actual derivation. So let's consider a long straight conductor carrying steady current. Now choose an ampere loop. So the ampere loop is such that it is at a R unit away from one of the centers. This loop is in a plane perpendicular to the wire. So this is 90 degree. Now if I happen to put the direction of current over here as I, as per your right hand rule at point P, say this is point P, what will be your direction of magnetic field? It will be tangential. Okay, perpendicular to the plane. Say this will be the plane. Let me do that with just a quick revision. This will be your imaginary plane. To that, perpendicular line will be in that direction, or if not, this direction. So we are going with the right because of the current direction and all of that, right hand rule. So we have it to be outward. That's dB. Now, from Biot-Savart law, the magnetic field at point P, which is R units away, is given by what? I don't have space over here. So let me write it here itself. B is equal to, or let me write it over there so that you guys don't get confused. B is equal to mu naught I by 2 pi R. Okay, agree? Now, what next? See, as the entire loop is at same distance of R, from the center, the magnetic field is same everywhere on the current loop. Why is that we are talking about this? Because I want, or we want, this integration to be simple. So if B is constant, take it out and just integrate dl, as simple as that. So we have chosen a current loop in such a way that it is R units away, it's circular, and the center is the wire. So with all of this factor, this makes sense. Agree? So as the entire loop is at the same distance R from the center, magnetic field is at the same everywhere on the current loop. Agree, guys? Okay. So basically, B is constant all over the loop. Now we'll look at the actual integration. B dl. So what about dl? dl, we assume the direction of integration in such a way that direction of integration we can assume in any ways. So this will be our direction of integration anti-clockwise. So our dl will be how? That too will be tangential, and here in this way and over here it will overlap. Yes, it will overlap. So our dl and dB are in the same direction. So what happens over here? So this two dot product will be equal to 1. Reason being, dl we have chosen the direction of integration such that dB, or in this case B and DL are parallel. Okay, so we have this to be B is common integration of DL, right? B is constant, that's what we have written over there. So we can write this as 1. So from 1, because of 1. And integration of DL is, entire loop is equal to how much? Yes, 2 pi r. Now, from 1, or in this case, I'll call this as 2 or A, something, anything, doesn't matter. So from A, what do we have? We have mu naught I by 2 pi r. So B is equal to mu naught I by 2 pi r. So 2 pi r, this and this will get cancelled, and we have mu naught I, hence proved. So again, the direction of integration, the direction of DL and DB, or in this case P, my bad, all of them we can handle, and the RHS, direction of current, is also related to the direction of integration and all of that. So you can see that the Ampere circuit law works. So you can prove this with any other, known B value for any other structure, but we have taken the simplest since we're getting introduced to the idea. Okay guys, so this is your proof.